All right, let's begin. Questions on the homework. Yep.
Through 29.
29. What does it say?
Derivative of 2x log base 10 to the radical x. 2x log base 10 to the radical x.
Like that?
Yep.
Okay. Who knows how to do that? Product rule, right? There are two functions here. You have 2x and you have log to the base 10 of radical x. Which you can actually simplify that, by the way.
1/2 ln x over ln 10.
Right, this radical you can think of as x to the 1/2 power. The laws of logarithm says we can bring that half down, it will cancel the 2, and so really we're just differentiating this. So you could have done that, make it a little bit easier, and now you do the product rule. You have x times log to the base 10. So differentiate the x, that's just 1, log to the base 10 of x, plus you leave the x, differentiate the log, what's the derivative of that? 1 over x ln 10, right, that's from the formula. So the x's would cancel, and so basically you have log to the base 10 of x plus 1 over ln 10. That's because of the rule. What?
Isn't it true?
2 where? Huh? Oh, I changed it from the beginning. So the radical I changed to the half power, and I can bring the powers down because of the log. So the half will cancel this 2. So I can use this. If you had gone through with the 2's, they would have ended up canceling out anyway. So that's that. Any questions on that? And here I just applied the rule. We know that the derivative, I asked this on the quiz, is just 1 over x ln a. So here my a was 10. So I just applied that rule. Other questions? No more? Was easy? 27? What is that?
LV, V's function equals tan for v squared.
V equals tangent to the 4th power of v squared.
Parentheses.
How is it? How did
The
it start?
function is L of V.
I love v
L of v.
equals 10 4 to the power of v to the power of 2.
Like that?
Yes.
And you wanted to find the derivative?
Yeah.
So L prime of v? Okay, how do we do that? Chain rule. So we have an inside function and an outside function. The outside function is tan, its derivative is secant squared. You leave the inside function intact. Multiply by the derivative of the inside function, which is, put the original back, times ln of 4 times the derivative of the power. So it's 2v. So nothing much to do here. I can rewrite it though. So something like 2v ln 4 times secant ln 4 times 4 to the v squared secant. So something like that. And again, here I'm using that rule that a to the u, the derivative is u prime, a to the u ln a. That's what I applied to get this. My a was the 4, my u was v squared. 17.
they gave you a graph of an exponential function, and they give you a
It looks
point.
like this.
Yeah, 1,6.
There's a point 1,6
Another one, 3,
and 324.
And it's only that there's a constant, and then
You say f of x equals c into the x.
F of x equals c,
A to the x.
a to the x.
Yeah, and you just want to find.
And you want to find what the
Yeah.
graph is. Okay. How do we do that? Right, just realize that each coordinate is x comma f of x, basically, right? So in the first case, the point 1,6 implies that when x is 1, the function output is 6. So I know that 6 is equal to c times a to the 1. And I also know that the point 324 means that 24 is the output whenever my x is 3. So what I can do is, this is equation 1, equation 2. What I can do then is I can take equation 2 and divide by equation 1. So in that case, I have 24 over 6 would give me CA cubed over CA. So 6 goes into 24 how many times? 4. The c's would cancel. A goes into a cubed, a squared times, which means a would be plus or minus 2. Of course, because it's a positive graph, I'm going to take a equals 2. And this means, since 6 is equal to c times 2 to the 1, therefore c equals 3. Therefore, my original graph is 3 times 2 to the x. And you can check your work just to make sure you have the right thing. When you plug in x equals 1, you get 3 times 2, which gives you 6. So that points works out. When you plug in x equals 3, 2 to the 3 gives you 8. 3 8's 24. And so that works out. Yeah. 23.
X is
to the x plus 5.
X to the 5th plus,
5 to the x. And then differentiate.
did they give it a name?
Oh, f of x is equal to.
We did this first, well, this just means, now before this we would have to do log differentiation and all that stuff, but we actually know nice formulas for these now, right? So this is just your old power rule. So this is 5x to the 4th plus, this guy we think of it as a to the x, where our a is 5. And we know the derivative of a to the x. It is a to the x times ln of a, which in this case is 5. And that's pretty much it. There's
I have a question. I left 5 to the x as e to the x ln 5.
Sure, yeah.
You can still leave that the same. Is that fine? Or is it wrong if I leave it?
So you mean if you rewrote this as e to the x ln 5?
Yeah.
That is correct. And then
But
you
then I left it like that in my answer. So
How
instead
do
of 5 to the x, I just left it e to the x ln 5 times ln 5.
It's the same thing.
Okay.
It'll look awkward, but it's the same thing.
Yeah, it's okay.
Yeah. So yeah, that's sort of the thing you do if you're in the test and you don't remember what the formula was. And you do that and you're like, okay, she figured it out. But yeah, you'd get it. You'd get the points for that. It's awkward, but it could be a little impressive because I figured out, oh, she forgot the rule, but then she derived it. You know, so it's kind of cool. Looks awkward, but it's cool that you'd know more than one way to skin a cat, so that would be nice. Other questions?
What's the integral of log term of x over x dx.
Okay, how did we do that?
U is log.
U equals
Log base 10.
log to the base 10 of x, which means our du is equal to
1 over x ln.
1 over x ln 10 by a rule already stated, dx, which means I can multiply both sides by ln 10 to get a 1 over x dx, which I have here. So the integral would become the integral of this guy's my u, and dx over x becomes ln 10 du. And so this is just ln 10 times u squared over 2 by the power rule. And so we have ln 10 times our u was this guy, so it's log to the base 10 of x squared over 2, and that would be the answer.
I have a question. When you differentiated u, you put 1 over x ln 10. Would you write 1 over log base 10 of x and leave it like that?
1 over log to the base 10 of x. What did you say?
You screwed up. That's the wrong answer.
What's wrong with that?
I got a different answer.
Oh, it's the wrong answer because you got it.
No.
Huh? What does the book say?
Oh, I got ln x squared over 2 ln 10.
You got ln x squared.
You don't multiply ln 10, you divide by ln 10.
They just rewrote it as
where-
ln x. They changed the base, so they changed it to ln x over ln 10, and they pulled out the ln 10 because
Using
it's
log
constant.
10 over x.
And you get u ln u.
So we could use the change of base.
Yeah.
They changed log base 10 of x
Okay,
to
so I mean, okay, so if we write this as ln x over ln 10 times x, that's what you mean?
Yeah. And then I did u equals ln x,
You can actually go from
and then which is 1 over x, but ln 10 is a constant, so you could take that out of the integral already, so it would be 1 over ln 10.
outside the integral.
Yeah, outside the integral, so it would be 1 over ln 10 integral ln x over
Yeah.
x.
Where did we mix up?
It's
Here we have this would be ln x over ln 10, right?
you multiply by ln 10. It's supposed to be 1 over ln 10.
You get the same answer if you use the change of base in your original answer. If you use the change of base log base 10 of x, you get
So,
the same answer.
I mean,
would
if
be
you-
top.
So you continue with this, right? So I'm not sure where you're mixing up. Okay, so we do that, and then you'd have 1 over ln 10, right? And we would have
U du.
u du, right? And so then you would have 1 over ln 10 times u squared over 2 plus c. But now this is, u is now ln, so this is ln x squared over 2 plus c.
You get the same answer.
Right, but then if you do a change of base of the ln, right? ln of x I can write as log to the base 10 of x over log over
Log base 10.
log to the base 10 of e.
I just left
And
it
that's-
at that.
It's the same thing.
And it'll end up being the same thing, but how did I overcomplicate it? That looks more complicated than that.
No, I left it the version above, I mean, the one above it.
You left it like this?
Yeah, so it'll be one whole fraction, it'll be ln x squared over 2 times ln 10.
It's the same thing. If you change log base 10 of x squared in in your original answer,
It's-
you get the same thing.
Yeah, it's gonna be the same thing. You can actually switch back and forth. Like I can do it here and I can get this one, right? So if I change this to ln x over ln 10, see the square will cancel one of these and you'll have one in the bottom. It's going to be the same thing here. Right? So ln 10 over 2. If I change the inside of mine, it'll be ln x over ln 10,
Oh, yeah.
right? Which would give me ln x squared over ln 10 squared. This would cancel one of those, and you can move it on. It's the same thing. Okay. Other questions? I know I know a formula to differentiate log to the base a of x. I wouldn't bother changing if I knew the formula. If I didn't know that formula, if I wasn't aware of this formula, equals 1 over x ln a, then I probably would have done this. But knowing that formula, I didn't see to do this. It's perfectly fine though. They're both the same. Other questions?
Can I do this? Can I bring down the 2?
No, you could not bring down the 2. So this here, notice that you cannot bring down the 2. What's the difference? Right. Looking at ln of x squared and ln of x squared are two completely different things. Right? One, you're squaring the argument inside the log. 2, you're squaring the whole thing. This guy I can bring the 2 down. This guy I can't. This guy is actually just ln x times ln x. Right? Where this guy is actually 2 ln x, which is ln x plus ln x. Right? They're different. So be careful of that. Where your parentheses are matters greatly. Other questions? Messed up. Okay. Are we done?
Are we getting our test back?
Yeah. I'll probably give that back at the end. So I have the homeworks and the previous 2 quizzes. No, 1. Yes. I have quiz 2, quiz 3, and your homework to give back. I'll give it back at the end. Other than that, we will move on. Well, this will seem sort of silly now, but I actually didn't write out the full worked out examples today, what I had last time. So let's just do those quickly. We all know the answers now, but we had a fire drill and we couldn't do this last time. So I actually, to find the derivative of log to the base 2 of x, I also asked you to find the derivative of log to the base 5 of radical x times x plus 1. I also asked you to find the derivative of log to the base 3, 10 plus 7 cosine x. Okay, quickly all together now.
ln x over ln 2.
Right, so you could change this to ln x over ln 2. And so your y prime would just be 1 over x ln 2, which is actually, we know this by a direct formula, that this is 1 over x ln 2. By the formula for log to the base a of x, the derivative. What about this one?
2x minus 1 times 2 log of 2x to the other 1.
You should consider all of this inside the log. That's how it's meant. Yeah, so does that change your answer, or what do you think? So if I apply the rule directly, I'm going to need to use the product rule in here, unless I multiply out.
Could you set it up, that portion as u, and then take the derivative of that on the side, and then plug it back in? Like follow the formula?
Yeah, we could do that, and follow the formula and do the product rule, or I could split the log up. This is just 12 log to the base 5 of x plus log to the base 5 of x plus 1. And then I don't need the product rule anymore. This is just 1/2 times 1 over x ln 5 plus 1 over x plus 1 ln 5. Didn't need that space. Okay, so how do we do this?
Split it over.
Can we split this up? No, there's a plus here. You don't have a rule for splitting a log across a sum, so what do? It's just chain rule, so it's just 1 over, this is now my x, ln 3 times the derivative of the x, which is minus 7 sine x. So just minus 7 sine x divided by ln 3 times 10 plus 7 sine x. At the end of this chapter, they made a statement that we'll prove when we talk about limits, but they defined the number e as a limit. I'm actually going to use it in a bit. It is n goes to infinity of, does anyone know?
1 plus 1 over n.
1 plus 1 over n to the n. I asked that on a quiz twice so far. So if you didn't catch it the first time, hopefully you caught it this time. That is the number e. Very important number. And we will derive that. It's not very hard to derive that. But we'll do it after we talk about limits, which I believe is 5.6. No, 5.8. We'll derive that in 5.8. But that is just a statement that they threw out there. And now we're moving on to 5.5, which you will need your handouts for. Yes, pass the homeworks up to the front. 5.5, we're going to look at exponential growth. Hopefully everyone remembered their handout because I don't have I probably have only one extra at the moment. Okay, let's do it. So pretty much everything you need to know is written here in concise form. Typically in a final, you don't have to really explain what you're doing. So you just, at the end of the day, you need to know the formulas and apply them. They give it them very straightforward like. So let's talk about that. Exponential growth and decay. Exponential growth. Let's deal with that first. This means a quantity increases at a rate proportional to its current size. Right, so that means if the quantity is described by p, it means p prime, the rate of change of p, is proportional to the current value of p, right? Usually this is a quantity that depends on time, so you think of this as functions of t, but I usually don't write it. So anything that has this sort of growth, we say it has exponential growth. A lot of things grow exponentially. Populations, for example, compound interest, certain compound interest problems will grow exponentially. But that's basically what exponential growth is. Anything that has this property, right? So how fast it's growing is actually dependent on what its current size is. So for example, you can think about population. Let's say R is called relative growth rate. This is all already in the handout. It's relative growth rate. It's also called the growth constant. Again, this is in the handout. You probably don't have to write it if you don't want. This is called the rate of growth. I know it's kind of confusing, but try to get the wording down. Right? Growth rate, rate of growth. Growth constant. Right? Especially here they emphasize relative, which means it's usually thought of as a percentage of the current population. So let's say, for a quick example, R equals 2. So I can say, how fast is the population changing when the population has 10 people in it? Well, if this is 2, that's 10, it means 20, right? So if I have a population with 10 people and the relative growth rate is 2, it means 20 new persons are being born ever so per unit time t, right? And let's say now the population increased to 100. Since this is 2, that means 200 people are being born every unit time t. The larger the population gets, the more babies you have, right? So it's not like the number of babies stay constant. The bigger your population, the more people having babies, the more babies you have. So you actually grow, the rate at which you're growing will actually increase as your current size is increasing. And whenever that happens, we say we have exponential growth. Do I want to derive the formula? So let's say p prime. I'll do it quickly. This isn't really emphasizing tau 2, so I'll just fly through it. P prime is thought of as a derivative with respect to time, right? Rate of change. So I can write this as dp dt. Using the Leibniz notation. Turns out derivative notations are really funny. You can actually treat them like fractions. So I could do something like dp and multiply both sides by dt. And then I could do something like divide both sides by p. And now you're like, oh, why not integrate both sides? Because I have those nice looking differentials. So then 1 over p, the integral of 1 over p is ln of p. Integral of r, since the variable is t, it's rt plus c. And this means, if I want to solve for p, what do I have to do? Right, raise both sides to the e, right? So I have p is equal to e to the rt plus c. This guy I can rewrite. P is equal to e to the rt plus c. This is just e to the rt times e to the c. E to the c is just another constant. Let me just rename that c. So now I know that p is equal to c e to the rt. Now let's suppose I actually know what the population is in the beginning. Let's say at time equals 0, I have P naught members in the population. This means if I plug in T equals 0 into this formula, P would be P naught e to the 0, which means your C equals P naught. And so finally you end up with the all-important formula. P is equal to P0 e to the RT. You won't have to know how to derive this until you get to a course like differential equations, and you'll derive a lot more complicated things than this. But it's important that you know this formula, which is called the differential equation. Again, this is in the handout. And this is the formula for P. Right? I call it the PERT formula, so I remember PERT, like the shampoo. But you guys are probably too young to remember.
No, that's zero. Minus. We got here minus RT.
That's for decay. We're doing growth, so we're getting bigger, right? If you had a minus, it means you're dividing by e to the t and e to the rt, and so you're getting smaller when t gets bigger, right? So I'm going to go over decay pretty soon, but that basically is growth. So p is the current population size, p naught is the initial population, r is the relative growth rate, t represents time in whatever units you're working. It could be months, years, days, hours, whatever. But that's basically the exponential growth. Now let's say something is growing and we want to know how long it takes to double that thing. So I use the notation in the handout, TD is called the doubling time. This is time for the quantity to double. If I were to find that time, how would I figure out what it is? So I know that P is equal to P naught e to the RT. So then for doubling, what does this mean if it's double? 2P? 2P naught, right? So I start with P naught. I want to figure out how long it takes me to get to twice that amount. Right? I can divide both sides by P naught. If I want to solve for T, I'd ln both sides. So I end up with ln of 2 is equal to RT, which means that my T must be ln 2 over R. And therefore we know that the time to double is ln 2 over R, right? Notice that there's nothing special about the 2. I could have figured out the time to triple, and I put a 3 here. It's ln 3 over R. Time to quadruple, ln 4 over R, right? It's a nice formula that tells you how many times you want to multiply the population by. That's going to be the time it takes to do it, right? So when you have a 2 here, that's the amount of time it takes to double, which leads you to that last formula, right? So the important things you need to know is the differential equation, P prime equals RP. That's an initial population. P naught will usually be given to you. Usually, not always, but you will get around that. The time to double is ln 2 over R. This is where the formulas came from. So I just listed them here, but this is sort of where they came from. Okay. Let's talk about decay. So again, I'm sort of running through this, but you don't really need to know how to derive these. You just need to know how to use them. But I thought it's cool for me to show you. We're going to use them in examples pretty soon. Okay. For decay, right? This means you have exponential decay when you're decreasing at a rate proportional to your current size. That gives you exponential decay, which means your growth rate is negative, right? Negative means decreasing. So you end up with that formula. A similar derivation will lead to the following: P equals P naught e to the minus RT. And that is for growth. For decay. So for decay, this is the differential equation. It has to be a negative coefficient for the P. And this will end up being what the general formula for the quantity is. Could be population, could be money, could be something else. Since this is decreasing, we're often concerned with what we call the half-life. You'll hear this mentioned all the time, especially in science context. Right? So this is time it takes for half the quantity to remain. Which means we can solve for that. How long does it take for me to have half of the original? I can just plug that in. So we'll do the same thing. Divide both sides by P0, ln both sides. So this gives me ln of 1/2 will be minus RT. This means that T would be ln of 1/2 divided by minus R, which happens to be, again, ln 2 over R. That we call TH, which is the time to become half. So I like writing it like this because you only sort of remember a formula once. It just depends on what context you're in, but it's going to be ln 2 over R. The time to become a third is ln 3 over R, so on and so forth. How does this become ln 2 over R?
ln 1/2 is negative ln 2.
Right, so ln 1/2 by our log rules is ln of 1 minus ln of 2. Log of 1 is 0. So this overall is minus ln 2. The minus cancels with the minus here. Okay, and so that's where these set of formulas came from.
I was just
Yes.
going to say also like 1/2 is 2 to the negative 1, and then you could also break it down.
Yeah, so you can also think of this as 2 to the negative 1, bringing the negative down. Yeah, tons of ways to get it. Yeah, that's where the formulas came from. You don't really need to know that, you just need to actually know them, right? Because they're not going to be given to you, so you have to memorize them. I don't remember if the syllabus said to skip compound interest.
It did.
Yeah. Omit.
Well, that sucks. Okay. It's something you should know anyway. So a lot of things are compounded, have compound interest, like your credit cards. Your interest is compounded, it's not simple interest. I have it here in case you want to read it up on it. But basically the compound interest formula, you can actually derive it. I'm not going to do it, but it will actually look like the exponential growth formula. So if compounded continuously. So let's actually just jump to the examples. So see these formulas in action. Okay. So we're going to do problems 1 and 2. I'm going to talk a little bit more about another law, and then we will do problem 3. This is for extra practice. I'm not going to go through these examples. These are actually from Math 205. They often do these problems on their finals as well, so I stole some other problems from there, just for extra practice. So let's do problem 1 from the handout. So, P of t is the current size of a population of bacteria at time t. At 10 a.m. there are 50 bacteria. At 3 p.m. there are 350 bacteria. Assume the rate of growth of the population is proportional to its current size, meaning we have exponential growth. And we have A, find the relative growth rate of the population. B, find the formula for P of t. C, what is the size of the population at 4 p.m. D, what is the rate of growth at 4 p.m. And E, when will the population reach 1500? Okay, ideas. How do we find the relative growth rate? Put all of it into what? Is 350 is what?
What it will be after 5 hours.
Well, we know we're using this formula, right? How do we know we're going to use that formula? Because of the last sentence. The rate of growth is proportional to its current size, right? Whenever that happens, you know you use the PERT formula, right? So that's going to be the hint to you. So, okay, you know that's the formula you're going to end up with. And what they're asking you for part A is the relative growth rate, which refers to the R, right? So we need to figure out what that R is. Do we know these quantities?
Is P not?
Right, we know P naught, it says we start with 50. So I can actually plug that in. 50. And that was at 10 a.m. Okay? So at 3 p.m. we have 350. How do I apply that? So P would now be 350, and when does that occur? When T equals 5, if we're measuring time in hours. Right? So we go from 10 a.m. to 3 p.m., that's 5 hours. Here I'm looking at T measured in hours. Right? So you can pretty much choose your units if it's not stated. Right? So we have that equation, and we simply now just solve it for R. How do we solve that for R?
Divide by 50.
Divide by 50.
7.
So 350 over 50 equals e to the 5r. So that's 7. Now you ln both sides. This means ln of 7 is going to be equal to 5r, which means r is going to be ln of 7 over 5, which is the answer to part A. Questions? Okay, move on. Part B, find the formula for P of t. So P of t is equal to P0, which P0, which we know is 50, e to the r times t. Now I know what r is, it's here, ln of 7 over 5 times t. That's good enough. We can actually simplify this formula, but I don't really care. All right, I can write this as e to the ln of 7, which becomes 7 raised to the t over 5 power, but I don't really care. That's good enough. Part C, what is the size of the population at 4 p.m.?
Plug in 6 for T.
Right, so at 4 p.m., this means t equals 6, right? That's 6 hours from the original time, which means the size is P of 6, which is 50 e to the ln of 7 over 5 times 6. If you know the formula, there's not much to do really. That's why I only have 3 examples. It's about knowing the formulas and being able to decipher the wording. So when you see things like grows proportional to its current size, you know that these are the set of formulas you need to use. And you need to know that R is called the relative growth rate, etc. So just some vocabulary and the formulas. What is the rate of growth? So rate of growth refers to what? Right, P prime is what rate of growth refers to. Okay, so I need to find P prime at 4 p.m. So I know that P prime of t is equal to R of P of t, right? Which means P prime at 4 p.m. means time is 6, is just R times P of 6. R, I already know, that's ln of 7 over 5. Times P of 6, I just found 50 e to the ln of 7 over 5 times 6. So that's 10 ln 7 e to the 6 over 5 ln 7. You don't use calculators, so you leave your answer like that. Questions? When will the population reach 1500? So when you see the word when, it means they're asking for what? Time. So I want the time when the population will reach 1500. So this is time when P, which is the current size of the population, is 1500. So now we know since P is equal to 50 e to the ln of 7 over 5 times t, we want 1500 equals 50 e to the ln over 7 over 5 times t. And now I solve for t. So you divide both sides by 50. What? And ln both sides. So 5 into 150 goes? Yes, it's late. Okay. So that will be, so, and it ends up being, so this means T would be ln of 30 over ln of 7 times 5 hours. Whatever that is. Any questions?
You know the 1500 population by 30 times the initial population, so could we just use the formula like T gamma? So we put T30 equal to.
Yeah, you could have done that. You could have put T is equal to ln of 30 over r. And you'd end up with the same thing. If you had noticed that though. Sometimes they put an ugly number here. But I made it easy. It's the principle that counts. Any other questions? Start to this so we can get to fun stuff, trigonometry. I'm so excited. Okay, half-life. So now we have a decaying substance. The half-life of a radioactive substance is 30 years. This means after 30 years, half of the substance will decay. You'll only have half of the amount left. Suppose we have a 200 milligram sample of this substance. P of t is the mass remaining after t years. Radioactive substances decay exponentially. So if you have uranium or plutonium in your basement, it decays exponentially. Okay, find the differential equation satisfied by P of t, which means we want P prime equals minus R times P, right? But we need to find the R to make this work. How do we get to the R? Right, you know that the half-life is equal to ln of 2 over r. The half-life, we are told, is 30. This means r is ln of 2 over 30. This means p prime is minus ln 2 over 30 times p. So there's a nice formula that gives us R. It relates it to the half-life, which we are told. P. The formula for P of t, we know that P of t equals P naught e to the minus RT, which means P is equal to, the initial was 200, we are told, e to the minus ln 2 over 30 times t. Right, 200 was given. that is in milligrams. How much will remain after 75 years? Right, how much is referring to the p? We want p when t equals 75. So this means p of 75 is 200 e to the minus ln 2 over 30 times 75, and that's whatever. You can plug these into your calculator to see a decimal answer, but we don't care. ABCD. After how many years will the mass be reduced to 1 milligram? We want t such that p equals 1. Right? So t such that p equals 1, this means that we want 1 is equal to 200 e to the minus ln 2 over 30 times t, which means we want 1 over 200 equals e to the minus ln of 2 over 30 times t. So I can ln both sides. This means minus ln of 200 equals minus ln 2 over 30, which means 30 ln 200 over ln 2 is equal to t. What is the rate of growth at the time of D? At the time when we have 1 milligram, what's the rate of growth? This is E. What they're asking is which one are they asking for? P prime when P equals 1. So this means I know that P prime of P is equal to minus R times P of T. This means the growth rate at that time, which I know what this is minus ln 2 over 30 times 1. So that's actually the growth rate. Any questions? Are we okay? Yeah. Sorry I couldn't make it harder. Sometimes life is easy. What can I tell you? Let's try to be a little bit more sophisticated. We're going to talk about a law that Newton himself figured out. It's called Newton's law of cooling, or Newton's cooling law. Basically, his law says that T prime is a constant times T minus T ambient. So T prime is the rate of change of temperature of an object. K is just a constant. It's the constant of proportionality. T is the current temperature of the object. This stands for the ambient temperature. Fancy name for surrounding temperature. It's not a law that you derive mathematically. He pretty much got this empirically, it's called, right? Meaning he tested a bunch of things, experiments, and measured their temperatures over time, collected tons of data, and he came up with this law. The rate of change of the temperature of an object is always proportional to the difference in temperature between the object and the surrounding temperature, right? So as it turns out, the hotter your coffee is, the slower it will get cooler. But the more you drink out of it, it will actually get cold faster, right? And Newton figured that out by having a lot of time on his hands and measuring stuff. Right? So as temperature drops, you get colder faster, is basically what this law says. The hotter you are, the slower you will actually lose your temperature. Okay? So we can actually solve this much in a similar way that we did before. We know that dt, d little t, is equal to k times t minus t a and b. I can again do what's called separation of variables. That's what the technical term for this is, where we try to separate these guys. So I put all the big T's on one side and all the little t's on the other side. And now again, it looks like a sort of derivative formula. Now we're calculus 2 students, we can do this. What's the derivative of that? The antiderivative of that. What? That's right, ln of t minus t ambient. Okay. And the integral of this is kt plus c, which means now I can raise both sides to the e. So this side is going to become t minus the ambient temperature is equal to a constant e to the kt, which means that your temperature at the current temperature is actually an exponentially growing thing. So that actually measures the temperature change of an object. C and K will be different depending on the object. These are constants. Certain objects will change temperature faster or slower than others depending on certain physical properties. That's not of concern to us at the moment. What is of concern to us is the example, the third example. A thermometer is taken from a room where the temperature is 20 degrees Celsius, and we move it to the outdoors where the temperature is 5 degrees Celsius. If I don't confuse any of the Americans with the Celsius, it doesn't even matter really. After 1 minute, the thermometer reads 12 degrees Celsius. What is the reading of the thermometer after 1 more minute, and well will the thermometer read 6 degrees Celsius? So, what do we know? So we're given some information. We know the temperature at time 0, right? So in the beginning, what's our temperature? It's 20. We also know the temperature after 1 minute, right? Which is 12. So we know after 1 minute, it cools from 20 degrees Celsius to 12 degrees Celsius. We know the surrounding temperature now, which is, it's 5, right? So we took this guy outside where it's 5 degrees Celsius. That's our surrounding temperature. And I want to figure out what's it going to be after 1 more minute. So how do I figure that out? Well, I know this formula. So I know since T is equal to CE to the KT plus the surrounding temperature, T t of 0 equals 20 means that this guy is 20 when my t is 0. So this just gives me C plus the surrounding temperature, which is 5, which means C equals 15. T of 1 is 12. That means the outside is, the current temperature is 12 when my T is 1. So now I have C e to the k plus the surrounding temperature of 5. But I already know what the C is. It's actually 15. So now we only have to find the k. So 12 is equal to C 15 e to the k plus 5. Okay, so how do we find k? Subtract the 5, 7, divide by 15, get 7 over 15. ln both sides. So you get ln of 7 over 15 equals k. This means our current temperature is given by 15 e to the ln of 7 over 15 t plus 5. So after one more minute, what's the temperature? We want t evaluated at what time? At 2. That's just 15 e to the ln of 7 over 15 times 2 plus 5. That's part A. Part B. When will the thermometer reach 6 degrees Celsius? So you just put 6 here. Want t, right? That's what when, such that t equals 6. Which means I simply plug in 6 over here. That gives me 15 e to the ln of 7 over 15 times t plus 5. And it's just algebra again, so this is 1 equals 15 e to the ln 7 over 15 t. This is 1 over 15 equals e to the ln 7 over 15 t. So this gives us minus ln 15 is equal to ln of 7 over 15 t. This means t would equal to minus ln of 15 over ln of 7 over 15. Does that answer make sense? Is time negative?
ln of 7 over 15 is negative.
ln of 7 over 15 is negative. Right? Remember, ln looks like that. This part is 1. 7 over 15 would be over here. So this is negative, so that negative actually makes everything work out. Right? So things like that you should worry about. Oh, it's time, isn't it? Right? But we're okay. Questions? Yeah, so there's probably a 75 to 80% chance of problems like this will be on your final, but they'll pretty much be just as straightforward as this. It's just a matter of knowing the formulas and applying them. Time flies when you're having fun. We're almost out of time. I guess we'll do a crash review of trig because we are going to be doing trig in the next section, and we're going to do a lot of trig later on as well when we go back to polar coordinates. Homework for 5.5 is due next time. When is our next class?
Next week.
Next week, Thursday. Right, so on Tuesday and Wednesday, we do not have classes. Next Thursday, we have regular class, but Friday is a Tuesday schedule. So next week, we have class on Thursday and Friday. So don't show up here Tuesday. Crash review of Trig. So after this, no one will have any excuse. I don't remember Trig, it was so long ago. I did it years ago in high school. Okay, let's talk about Trig. You should know this already. You probably don't even need to take notes.
Question about the schedule next week. So since Friday's running on Tuesday schedule, I actually work Fridays, and I know you give out quizzes once a week. So is it going to be guaranteed on Thursday?
Yeah, I'll give it on Thursday.
There's a holiday.
Yeah.
Thursday.
Muslim holiday.
Yeah.
Thursday is a holiday?
Yeah. But Tuesday and Wednesday is a Jewish
No,
holiday.
Tuesday, Wednesday.
But aren't we here on Thursday?
Yeah, but it's not official, but it's a holiday.
What does that mean? Like some people are not showing up on Thursday?
Yeah, so okay, that means everyone.
We'll figure it out. Okay. Everything since the last time. So the stars of Trig are sine x and cosine x, right? Everything comes from sine x and cosine x. What are sine x and cosine x? Basically, you have the unit circle, right? So circle radius 1 centered at the origin. Sine x and cosine actually gives you the coordinates along this circle. Probably call it theta. So sine, cosine theta, sine theta actually give you the coordinates on this circle, where if you connect it to the center, theta would be the angle here. If you want to figure out what the x coordinate is, it's given by the function cosine. If you want to figure out what the y coordinate is, it's given by the function sine. So we can know a few elements here. So this would be the coordinate 1, 0, right? This would be the coordinate 0, 1. This would be the coordinate -1, 0. This would be the coordinate 0, -1. We also know this angle. This is theta equals 0, right? This is theta equals pi over 2. This is theta equals pi. This is theta equals 3 pi over 2. So we automatically know some values just by knowing there's a unit circle, right? I know that, for example, the cosine of 0 is 1, the sine of 0 is 0. Cosine of pi over 2 is 0, sine of pi over 2 is 1. Cosine of pi is -1, sine of pi is 0. Cosine of 3 pi over 2 is 0, sine of pi is -1. From these, you can sort of chart out what these graphs look like. So y equals sine x looks like the following. Right? It actually continues forever, right? But they usually only talk about what's called the principal period. The maximum here is 1. The minimum here is -1. It hits 1, as you can see from the unit circle, at pi over 2. It's 0 at pi. It's -1 at 3 pi over 2. It's here at 2 pi. This is called the sine function. It repeats. Notice that sine of n pi gives us 0, right? So if you continue this pattern, minus pi, -2 pi, -3 pi, it's all going to be 0. 0 pi, 2 pi, 3 pi, 4 pi, blah, 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 all going to be 0. Sine is 0 at these values, right? So if you ever want to know when sine is 0, it will always be 0 there. The function y equals cosine. It starts at the peak. It's up here. Again, maximum is 1, minimum is -1. Hits 0 at pi over 2. It's the minimum at pi. Hits 0 again at 3 pi over 2. And hits the maximum at 2 pi. And now we know that cosine of n pi over 2 gives us 0, where n is an odd integer. Right? For sine, n is any integer. Integer just means whole number, right? So cosine of pi, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, that works. Here it works for pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc. Right? You also know that cosine of 2n pi is always going to be 1. So we know those from the graphs. We can use Pythagoras' theorem to discover some nice values for these two functions. I don't like to use the triangles once we actually figure them out, though. I like to represent these angles in a table, which is easy to fill out, right? So you put theta, this is sine theta, this is cosine theta. These are the special angles. 30 degrees is one of them, which we can write as pi over 6. 45 degrees is the second one, which we can write as pi over 4. 60 degrees is the last one, which we can write as pi over 3. And anyone knows how to fill out the table? 1, 2, 3. 3, 2, 1. Take the square root of everybody and divide everyone by 2. Right? So we know that sine of pi over 6 is a half, cosine of pi over 4 is equal to 2 over 2, cosine of pi over 3 is a half, etc. Right? 1, 2, 3, 3, 2, 1, radical everybody, divide by 2. Okay, right, so that's how when someone, asks me, oh, Jhevon, what's pi over 6? And I'm like, it's a half. And you're like, how do you know this so fast? Because in my head, I know pi over 6 is 30, sine starts with 1, 2, 3, it's going to be the 1 over 2, right? It's just like a picture you have in your head. It's an easier picture than the two triangles I always see people drawing. I don't know why they draw those triangles. It seems complicated to me. Let's use Pythagoras' theorem in your head. Why would you do that? So there's this table, right? That gives you all these nice angles. You're expected to know these like that, right? Now, what if we can also find the value of the trig functions at any multiples of these angles? How do we do that? So let's say we want to find sine of 5 pi over 6. Right? So it's not just pi over 6, it's 5 pi over 6. Right? But remember, the values just repeat, right? So it's never going to exceed sine of pi over 6. In fact, it's going to be plus or minus sine pi over 6. Basically, whenever you see anything like this, you ignore the coefficient and look at the special angle. And you sort of figure it out. So how do we know? So sine of 5 pi over 6 is going to give you the same thing as sine of pi over 6. How do you know if it's plus or minus? You figure out the quadrants, right? So remember how the quadrants work. All students take crack, right? So not everyone takes calculus, come on. Okay, so all trig functions are positive here. Sine and cosecant are positive here. Tangent and cotangent are positive here. Cosine and cosecant are positive here. By the way, this all comes from the unit circle, right? In this region, your x-coordinate is positive, but your y-coordinate is negative, right? It all goes back to the unit circle. So that's how you know how the signs work. So basically what happens is when you see something like pi over 6, what you do is you go to the unit circle again, cut it in two, here's 0, here's pi, right? Pi over 6 means you divide pi into 6 pieces, right? So I take the top half, I'm going to cut it in half, and then cut each half in 3. Right? Do the same thing here. Right? Now I want 5 pi over 6s. Each of these pizza slices is a pi over 6, right? Take 5 of them. 1 slice, 2 slice, 3 slice, 4 slice, right? 5 slices. End up in the second quadrant. Sign is positive in this quadrant. So this is plus sine pi over 6, which we know the answer is a half, right? So if I do something like cosine 7 pi over 3. Unit circle, 0, pi. Pi over 3 means divide pi into 3 pieces. Take 7 of them. 1, 2, 3, 4, 5, 6, 7. End up in the first quadrant. So cosine of 7 pi over 3 is just positive cosine pi over 3, which altogether now is also 1/2. Now, we can also ask about pi over 4. So let's do something like sine of 5 pi over 4. So again, This is 0, this is pi. Power formula is divide pi into 4 pieces. Take 5 of them, right? There are 5 pi over 4s. 1, 2, 3, 4, 5. Puts me in the third quadrant. Sign is negative here. So it's just minus radical 2 over 2. Okay? All right. So we know what sine, cosine are at every multiple of pi, at every half multiple of pi, and at any multiple of 30, 60, or 45, right? Just by knowing the table and the graphs. Huh? What else do we need to know? We can define other trig functions. So we can define the tangent function, right? As sine over cosine. We can define what's called the cosecant function. That's 1 over sine. We can define the secant function.
Professor, can I just take my quiz and leave? I have a workshop to attend to right now.
Oh.
I'd like to give.
Or you could pick it up next
time.
time. Oh, do we actually, we're out of time?
Yeah, 7:45.
Okay. All right, we'll leave. We'll maybe pick up, or maybe just review Trig on your own, I guess. Yeah, I have them if you want to take them. We'll stop there for now. No, I don't care.
Okay, thank you.
P1. I think we can stop now.